Welcome back to Explain the Show that takes those brain-twisting topics and makes them, well, a little less twisty. Today we're tackling something that's really fundamental to how our digital world works: external data structures.
Think about it this way. What happens when the amount of data you have just won't fit in your computer's memory? It's like you're trying to cram a whole library's worth of books onto a single desk.
Okay, I'm intrigued already. So how do we actually deal with this data overload?
Yeah,
I mean, our computers are powerful, but there's got to be limits.
exactly. And that's exactly where external data structures come in. They're like these giant, super organized warehouses for all your data, living on hard drives or SSDs where there's way more space.
So we're basically outsourcing the storage to these warehouses. But I'm guessing there's got to be some kind of trade-off, right? Accessing data in a massive warehouse can't be as quick as just grabbing something right off your desk.
You're absolutely spot on. Accessing data that's stored externally is always going to be slower than working with it directly in your computer's memory. That's why efficiency is like the golden rule when we're designing these external data structures.
So it's not just about storing the data, it's about being able to find it fast when you need it. Now, I know we're going to dive into some specific types of external data structures like B-trees and hashing. But before we get there, I'm curious, have you ever had that moment where your computer just choked on a large file or data set? Let us know down in the comments.
Absolutely. And those are the exact moments that highlight why these structures are so crucial. We'll be focusing on two main families: those based on tree structures like B trees and B plus trees, and then those that use hashing like extendable and linear hashing.
Okay, so let's unpack these tree structures first. Now, I vaguely remember learning about binary search trees way back in my computer science days. Is there a connection here at all?
You bet. B trees actually build upon that concept of binary search trees, but they're specially optimized for that external storage we are talking about. Think of each node in a B tree as a storage container in our warehouse analogy.
So instead of individual data points, we're storing like these chunks of data in each of these containers.
Exactly. And to make things even more efficient, each container is holding a whole bunch of sorted keys. Think of it like an index in a library pointing you to the right section.
Okay, so we have these containers packed with sorted keys, but how is it all organized within the warehouse?
This is where it gets really smart. B trees are what we call balanced, meaning all the containers on that bottom level of our warehouse are the same distance from the top. This balance makes sure that no matter what data you're looking for, the retrieval time is pretty consistent.
So it's like a perfectly organized library where you can find any book within a few minutes no matter where it is. That's really impressive. But what happens when you need to add new data to our already packed warehouse? Things could get pretty messy, right?
That's a great question. In a B tree, when a container or node gets full, what we do is we split it and create a brand new one, spreading out some of the data. Think of it like reorganizing a bookshelf to make room for more books.
That makes sense, but wouldn't splitting a node like that and making a new one mess up the balance we were just talking about? How does the system keep things so evenly distributed?
That's the genius of B trees. Sometimes this splitting process actually involves adding a whole new level to our warehouse, building upwards if we have to maintain that perfect balance. And all of this is happening behind the scenes without you even knowing.
Wow, so it's like this self-organizing warehouse that just grows as your data grows. Don't forget to follow Explain for even more deep dives into this amazing world of data structures and algorithms. Now, all this splitting and moving of data, wouldn't that take a ton of time? How does the system deal with all that extra work?
That's a valid concern. The way the system is designed, it tries to do these operations as little as possible, making them as streamlined as we can, remember. The goal is to reduce those trips we have to make to the warehouse, because that means faster data retrieval in the long run.
So B-trees are all about that balance between how much you can store and how quickly you can find it. But is there any way to speed things up even more? In the world of data, speed is everything, right?
You're absolutely right. And that's where B plus trees come in. They're kind of like B trees, but with a special twist. Imagine having this central directory at the very bottom level of our warehouse.
Intriguing. What's the purpose of that central directory?
So in B plus trees, all the actual data lives in this directory at the bottom level, while the upper levels are basically a roadmap guiding you to the right spots super fast.
So instead of data potentially being scattered all over the different levels, everything is in this central hub. That sounds like it would make searches lightning fast.
Exactly. This kind of structure makes searching and grabbing data even faster, especially for those common search operations. It's like having the super efficient index right at the bottom of the warehouse, letting you bypass a lot of unnecessary searching around.
So B-plus trees are like the express lane of data retrieval. Can you give us an example of where this speed would be absolutely essential in real life?
Think about online shopping. When you search for a product, you want those results to pop up instantly. B-plus trees play a big role in making that happen.
I see. That makes perfect sense. Now I'm really starting to understand why choosing the right data structure is so important. It's like picking the right tool for the job. You wouldn't use a hammer to tighten a screw, right?
Perfect analogy. Now, are you ready to leave our tree-based warehouse and check out a completely different system?
Absolutely.
Okay.
I'm ready for a change of scenery. What's next on our data structure adventure?
Let's jump into the world of hashing. Imagine assigning this unique code to every single piece of data and using that code to figure out exactly where it goes in the warehouse. That's the basic idea behind hashing.
It's like giving each piece of data its own GPS coordinates in the warehouse.
Mhm.
Sounds super efficient. But how do you even come up with these unique codes in the first place? Is there like a special formula or something?
There are all kinds of hashing algorithms out there that create these unique codes based on the data itself. And just like with those tree structures, there are different ways to implement this whole concept. Two popular ones are extendable hashing and linear hashing.
Okay, break those down for me. Extendable hashing first. What's the main idea there?
Think of extendable hashing like this dynamic system where the warehouse map actually expands as more data comes in. It's like adding new streets and buildings to a city as it grows.
So it's this flexible system that adapts to how much data you're throwing at it. That seems incredibly useful in a world where we're generating more data all the time.
Precisely. And then there's linear hashing, which takes a slightly different approach.
I'm all ears. Tell me about linear hashing.
It's like having this organized, step-by-step way of filling up our warehouse, and then we use these overflow areas when things get too full. It's kind of like having a plan for where to put everything, but with a little bit of wiggle room built in.
So a more structured approach, but with the ability to adapt as you go. Love learning about all this intricate data stuff. Make sure you're following Explain so you don't miss out on any of our future episodes. We've covered B trees, B-plus trees, even dipped our toes into hashing. But I have a feeling this is just the tip of the iceberg. What are some of the really cutting-edge advancements in all of this? What's coming next?
You're exactly right. This world of external data structures is massive, and it's always changing. Researchers are coming up with new ways to manage and access data all the time. One area that's really hot right now is developing data structures that can handle the unique challenges of what we call big data.
We hear that term big data thrown around a lot. What does it actually mean in this context?
It's basically any data set that's so huge and so complex that traditional data processing techniques just can't handle it.
So we're not just talking about size, we're talking about data sets that are incredibly diverse and messy too.
Exactly. Think about the data coming from social media or sensor networks or scientific research. We're talking petabytes of information being generated every single day.
It's mind-boggling how much data we're producing as a society. So how do external data structures help us make sense of this deluge of information?
Researchers are creating these new data structures that are specially designed to handle the sheer scale and the complexity of big data. These structures often rely on what we call distributed systems, where data is spread across multiple machines.
So instead of one giant warehouse, we're now talking about a whole network of interconnected warehouses.
Precisely. And these distributed data structures have to be incredibly efficient at coordinating access to data across all these different locations.
That sounds like a massive logistical challenge.
It is, but it's also an incredibly fascinating area of research with a ton of potential. These advancements are what's allowing us to make new discoveries and gain new insights that were just impossible before.
It's exciting to think about all the possibilities. Are there any other trends or challenges that you see really shaping the future of external data structures?
Absolutely. The rise of cloud computing is having a huge impact. As more and more data moves to the cloud, we need data structures that can work seamlessly with these distributed environments.
So it's not just about managing big data, it's about making it accessible and usable in the cloud too.
Exactly. And of course, security is another huge concern. With so much sensitive information stored digitally, we need external data structures that prioritize privacy and data protection.
So it's this constant balancing act between efficiency, scalability, and security.
That's a great way to put it. The whole field of external data structures is all about finding the right balance to meet the ever-changing demands of our digital world.
It's been incredible exploring all these concepts. I feel like I have a much deeper appreciation for all those hidden structures that are actually powering our digital lives. Can you think of any real-world applications where database speed is just absolutely crucial? Share your thoughts down in the comments.
And remember, this is just scratching the surface. There's a whole universe to explore within the world of data structures and algorithms. Now that we've gotten a handle on the basics of B trees, B plus trees, and hashing, let's shift gears a bit. Let's look at how these external data structures actually play out in the real world.
I'm all about getting practical.
Hmm.
We've been talking warehouses and directories, but I want to see how this all connects to stuff we use every day.
You got it. These structures aren't just some abstract concept. They're the backbone of a lot of what we do online. Take databases, for example. They lean heavily on external data structures to manage and find information quickly.
Okay, databases. Now that's something we all use, whether we realize it or not. What always blows my mind is how fast we expect those search results. I type something into Google and boom, millions of results in a split second. How is that even possible?
That speed is really a testament to the power of efficient data structures and algorithms doing their thing behind the scenes. But it's important to remember that not all databases are the same. Some are built for speed when it comes to specific types of searches, while others might focus on efficient storage or making sure the data is super reliable.
So it's about choosing the right data structure for the specific job you need to do.
Exactly. Let's say we're talking about a database for an online store. When you search for a product, the database has to find it instantly or you're going to click away and go somewhere else.
Totally. Nobody's got time to wait for ages for a page to load these days.
Right. So in that scenario, a B plus tree would be a great choice. Remember that central directory we talked about? It's all about fast searching and retrieval, perfect for finding products based on keywords or categories.
So it's like this perfectly organized stockroom where you can instantly find any item no matter how much stuff you have. But what about those times when speed isn't the only thing that matters? Are there situations where other data structures might be a better fit?
Definitely. Think about a bank that's dealing with millions of transactions every day. In that case, accuracy and reliability are absolutely critical.
Yeah, even the smallest error could have huge consequences in that kind of situation.
Absolutely. So in cases like that, the database might prioritize making sure the data is rock solid over pure speed. B trees, with their balanced structure and their way of handling data updates, could be a really solid choice.
So it's a balancing act between speed and reliability, and the choice depends on what the application actually needs. Kind of like choosing the right tool for the job. You wouldn't use a hammer to tighten a screw.
A perfect analogy. Now let's switch gears and talk about file systems.
You mean like how our computers organize all our files in folders? I've always wondered about that. It seems so simple from a user's perspective.
It might seem that way on the surface, but trust me, there's a lot of complexity happening behind the scenes. When you save a file, your operating system has to figure out where to put it on your hard drive and how to keep track of it. And guess what plays a huge role in that whole process?
I have a feeling it's those external data structures we've been chatting about.
You got it. B trees, or variations of them, are really common in file systems to keep that directory structure organized.
So when I click on a folder, the system uses a B tree to quickly locate all the files inside.
That's the basic idea. The tree structure lets the file system manage all those hierarchies of files and folders efficiently, so you can access your stuff whenever you need it.
It's amazing how all these data structures are working behind the scenes, making our digital lives possible. We're using them constantly without even realizing it. Now we've focused a lot on B trees and all their variations. What about hashing? Where does that fit into real-world applications?
Hashing is like a Swiss Army knife. It's incredibly versatile and pops up in a ton of different areas. One big one is caching.
Caching, is that like those annoying browser caches that sometimes make websites display wrong?
Same concept, but caching is actually a really powerful way to boost performance. Let's say you're browsing the web and you visit the same website a couple of times. Instead of going back to the server to get the website's data every single time, your browser can store a copy of it in what we call its cache.
So the next time you visit, your browser loads the page way faster because it doesn't have to go all the way back to the server. That's pretty smart. But where does hashing come in?
Hashing is crucial for managing the cache efficiently. When your browser gets data from a website, it uses a hashing function to create this unique key for that data. That key is then what's used to store the data in the cache.
So each piece of data in the cache gets its own ID tag thanks to hashing. Makes sense. But how does the browser actually retrieve that data from the cache using these keys? It seems like finding a needle in a haystack.
That's where the magic of hashing really shines. When you request a website that's already in the cache, the browser uses that same hashing function on the website's URL. That generates the same unique key. Then it uses that key to go straight to the cache data No need to search the whole cache.
Ah, so it's like a direct line to the information you need. No searching, no waiting. Hashing really streamlines that whole caching process. I'm starting to see why it's such a popular technique.
Exactly, and caching is just one example. Hashing also plays a huge role in how passwords are managed. Instead of storing your actual password, which would be a security nightmare, websites use what's called a hashed version of it.
So even if someone hacks into the database, they wouldn't be able to actually see my password.
That's the idea. The hashing function turns your password into this unique scrambled string of characters that can't be reversed. When you log in, the website hashes the password you type in and checks if it matches the stored hash. If they're the same, you're in.
That sounds way more secure than just storing passwords in plain text.
Yeah.
Hashing really is a multi-talented tool for boosting both security and efficiency.
It really is. And as we keep generating more and more data, having these efficient data structures and techniques is only going to become more important.
It's mind-blowing how these concepts that seem so abstract actually have such a massive impact on our digital lives.
Mm.
We've gone from B trees to hashing and their real-world uses. But I have a feeling there's still a lot more to uncover. Where to go from here?
You're right, we've barely scratched the surface of what external data structures can do. This field is constantly evolving as we face new challenges in our data-driven world.
So what's next on our data structure adventure? Any other exciting areas we should explore?
Absolutely. Let's dive into the world of distributed data structures. Remember those networks of interconnected warehouses we talked about? Well, managing data across these distributed systems brings a whole new set of challenges and opportunities to the table.
Distributed data structures. That sounds like we're heading into uncharted territory. I'm intrigued. Tell me more.
Imagine a massive social media platform, right? Billions of users creating tons of data every single day. Storing and managing all that on just one machine would be impossible. That's where distributed systems come in. The data is spread out across tons of servers.
So it's like having a global network of warehouses, each one handling a chunk of the data. But how do these systems make sure that data can be accessed quickly and reliably across this huge network?
That's where those distributed data structures step in. They're specifically designed to handle all the complexities of data that's spread out, making sure it's consistent, can handle failures, and is available pretty much all the time.
Consistent, fault-tolerant, and highly available. Those sound like really important things to consider in a distributed environment. Could you break those down for us?
Sure. Consistency means that everyone sees the same data no matter which server they're connected to. Fault tolerance means that the system keeps chugging along even if some servers go down. And high availability makes sure the data is accessible almost all the time, even during maintenance or upgrades.
Those are some impressive features. It's amazing how these systems can handle such complex situations. But what about the user experience? Do these distributed data structures cause any noticeable delays?
That's a valid question. Latency, or the time it takes for data to travel across the network, can definitely be a challenge in these distributed systems. But there are some clever tricks we use to minimize those delays, like replicating the data and using caching.
So it's about strategically placing copies of the data closer to the users who need it and using those caches to hold on to frequently accessed information.
Smart. It's like having local distribution centers to serve a global customer base.
Exactly. And those optimization techniques are always evolving because we need those applications to be faster and more responsive.
It's incredible how much innovation is happening in data management. It's like a constant race to keep up with the ever-growing volume and complexity of data. Absolutely. And that race is fueled by all the amazing opportunities that big data offers. If we can efficiently manage and analyze this huge ocean of information, we can unlock new insights, make smarter decisions, and maybe even solve some of the world's biggest problems.
So these distributed data structures aren't just about technical efficiency. They're about giving us the power to actually use big data to make a difference.
That's a pretty powerful thought. Now, I'm curious about the specific types of distributed data structures out there. Are there any big names we should know?
Definitely. One that comes to mind is the distributed hash table, or DHT for short.
Distributed hash table. That rings a bell. Is it related to the hashing we talked about earlier?
You got it. It's essentially like a decentralized version of a hash table, where the data is spread across lots of different nodes in the network.
So instead of having one central server managing everything, the responsibility is shared by multiple nodes. That sounds like a super scalable and fault-tolerant approach. Exactly. DHTs are designed to handle situations where nodes might fail. If one node goes down, the system can automatically shift the data to the other nodes that are still working.
That's impressive.
Ugh.
It's like a self-healing network that can adapt to whatever's thrown at it.
Mm.
But how does the system actually find data in this kind of decentralized setup? It seems like it would be tough to find a specific piece of information without a central index.
That's where the clever design of DHTs comes in. Each node in the network is in charge of a certain range of keys. When you want to store or find data, the system uses that hashing function to figure out the key for that data and then sends the request to the node responsible for that key.
So it's like having a network of expert librarians, each one knowing exactly where to find specific books in a giant library. You tell them what you're looking for and they point you in the right direction. It's a brilliant analogy.
It really captures the essence of how DHTs work. This decentralized approach has a lot of advantages: scalability, fault tolerance, and even resistance to censorship.
Scalability, fault tolerance, and resistance to censorship. Those are some seriously powerful attributes. It seems like DHTs are perfect for applications where decentralization is super important.
You nailed it. DHTs are used in a bunch of peer-to-peer systems, like those file-sharing networks and even cryptocurrencies.
File sharing networks and cryptocurrencies. Now, those are applications that truly benefit from being decentralized. It's amazing how these distributed data structures are shaping the technology landscape.
It really is an exciting time to be exploring the world of data management. We're constantly pushing boundaries to keep up with the growing amount and complexity of data and to unlock all of its potential.
Okay, so we've wandered through forests of bee trees, navigated those hashing highways, and even explored the vast landscapes of distributed data structures. But this data structure world, it's like a never-ending universe, right? What other fascinating structures are out there waiting for us to discover?
You're absolutely right. There's always something new to learn and explore. Let's dive into the realm of graph databases. They offer a really unique way of looking at data, not just as individual points, but as part of a web of relationships.
Graph databases. Okay, that sounds intriguing. I kind of remember graphs from way back in math class, but how do they apply to data?
Think of it like a social network. Each person is a node, and those friendships between them, those are the edges that connect the nodes. A graph database stores information this way, making it perfect for understanding those really complex relationships.
So instead of those rows and columns in a table, we've got nodes and connections. That's a really visual way to think about data. What kind of applications would really benefit from this approach?
Imagine a social media platform trying to recommend new connections. A graph database can easily trace that web of friendships and suggest people you might know based on shared connections. It's all about understanding the links between different pieces of data.
Ah, so it's not just about storing the data, it's about uncovering those hidden relationships within it. That's pretty powerful stuff. I can see how graph databases could be used in tons of different scenarios. Any other examples come to mind?
Oh, absolutely. Think about fraud detection. A bank could use a graph database to analyze transactions and spot those suspicious patterns. Multiple accounts linked to the same device or sudden unusual spending, those connections become so much clearer when you visualize them as a graph.
That's a great point. It's like having a detective who can see the bigger picture and connect all those dots. Are there any other areas where graph databases are making a big impact?
They're gaining a lot of traction in knowledge management and even drug discovery. Imagine a database of all those scientific papers where you can explore the connections between different research articles, authors, and concepts. Or a database that maps the relationships between genes, proteins, and diseases to help speed up the development of new drugs. The possibilities are pretty mind-blowing.
It's amazing how these data structures are helping us solve real problems in the world. It seems like the more we understand about those relationships within data, the more we can learn about the world around us.
Exactly. And speaking of understanding the world, let's switch gears to another type of database: spatial databases. These are all about location, location, location.
Spatial databases. That sounds like something straight out of a sci-fi movie. What are they used for?
Think maps, GPS navigation, location-based services, anything that deals with geographic information. Spatial databases store and analyze data about where things are and what shape they have in space.
So when I'm using Google Maps to find the nearest coffee shop, I'm basically using a spatial database.
You got it. Spatial databases power all those mapping and navigation apps we use every day. They store information about roads, buildings, points of interest, even terrain, so we can find our way around.
That's so cool. It's crazy to think about all this spatial data that's constantly being used behind the scenes to make our lives easier. Are there any other interesting applications for spatial databases?
Definitely. They're used in urban planning, environmental monitoring, logistics, even precision agriculture. Imagine optimizing delivery routes using real-time traffic data or tracking the spread of a disease outbreak geographically. Spatial databases give us a whole new way to see and analyze data.
It's fascinating how these data structures help us make sense of and interact with the physical world. We've covered so much ground today, from those bee trees to graph and spatial databases. It feels like we've just scratched the surface of this massive and complex world.
You're absolutely right. There are tons of other specialized data structures out there, each one fine-tuned for certain tasks and challenges. The whole field of data structures is constantly evolving as we try to keep up with the ever-growing amount of data and to find valuable insights within it.
It's incredible how these structures, which are often hidden from view, are really the backbone of our digital lives. They're what power our search engines, our social networks, our maps, and so much more.
And as we keep generating more and more data, understanding and choosing the right data structures will become even more crucial. They're the key to unlocking the real power of data and driving innovation in every single field.
This deep dive into external data structures has been truly eye-opening. I think our listeners have learned a ton today and gained a new appreciation for all those complex systems that make our digital world work. Don't forget to follow Explained for more explorations into the fascinating worlds of technology, science, and culture.
If there's a specific topic you're dying to know more about, leave a comment below. We're always excited to dig into new subjects and share those aha moments with you.
Until next time, keep those brains curious and those data structures organized. This is Explained, signing off.